Okay, well, hi, I'm Travis English with Kaiser, and thanks for checking in today. In the last 9 months, HVAC engineers have been doing a lot of things to our systems in the name of infectious aerosol control. We've seen hundreds of millions of dollars going into aerosol controls this year, and then hundreds of articles, thousands of words of recommendations in the industry press. Today, I want to take a couple steps back because the vast majority of activity in 2020 has been uncalculated, non-comparative, and unvalidated. Uncalculated, meaning that we're not calculating or quantifying the effects that we want to produce. Non-comparative, in that, for example, a filter, a UV system, and some increased outside air could all be used to the same end, but we're not comparing them to each other in any meaningful way. And then finally, unvalidated, in that we're not measuring the effects we're supposed to have on the physical environment. And so today I'd like to move that conversation forward practically by reviewing calculations and comparison and validation methods that we all might want to be familiar with. So in terms of particulates and bioaerosols, infectious aerosols are particulate matter. So in your air quality district, you report PM10, particulate matter 10 microns or below, PM 2.5 for particulates less than 2.5 microns. And then there's some movement afoot to start reporting PM 1, particulate matter less than 1 microns. Those units are all in micrograms per cubic meter. Then we have gas contaminants like CO2 or oxygen, O2, or volatile organic compounds. Typically use these unitless metrics. 1 part per million is one contaminant part for every 10 to the 6 units of air, or 10 to the minus 6. 1 part per billion is 10 to the minus 9. 1 part per trillion, 10 to the minus 12. 1 part per quadrillion, 10 to the minus 16. 1 part per billion, by the way, is 1 teardrop in an Olympic-sized swimming pool. And then 1 part per trillion is 1 teardrop in 1,000 Olympic-sized swimming pools. So to kind of put these metrics, to equate them to each other, 1 cubic meter of air is 1 kilogram, 1.2 kilograms actually, but we'll round to 1. So in grams, 1 microgram is 10 to the minus 6 grams per cubic meter, 10 to the 3 grams is a kilogram. So that comes up with 10 to the minus 9, or 1 part per billion. The other way that we measure particles in air is the quantities per cubic meter. So we state the diameter of the particle population and then the quantity of particles, number per meter cubed or N per meter cubed. This is particularly popular in clean rooms. The ISO 14644 standard is a way to classify how clean air is. This equation gives the maximum number of particles per cubic meter based on the diameter of the particle. So, for example, for 0.3 micron particles in a class 6 clean room, we'd have a maximum of 42,256 particles per cubic meter. And you can see that in the equation, if you change the class, it just changes the power of 10. And by the way, for reference, normal atmospheric air without fires is going to be about class 8 or class 9. So we can't measure bioaerosols in real time. We actually have to extract air from a space, send it to a lab, and then get it back. That takes about 24 hours, although that time is improving all the time. The units that you'll see on those lab results are going to be in colony forming units, or CFU per meter cubed. Sometimes you'll see plaque forming units, which is PFU per meter cubed. And just this year, we've been seeing measurements of airborne concentrations in like viral particles. So the actual number of virus copies per cubic meter. That technology is new and rising relatively quickly. So infectious aerosols don't arrive in a room by any other means than people. They come in here, they come in with people in the Trojan horse of our respiratory fluids. When we breathe, we put about 1 nanoliter of fluid per minute into the air. When we speak, that's about 10 nanoliters per minute. When we cough, it's about 100 nanoliters of fluid that we put out per cough. So if you cough 10 times a minute, that's about 1,000 nanoliters of fluid per minute. It's those fluids that contain the infectious aerosols. So they might have 10 to the 4 or 10 to the 6 virus copies per milliliter of fluid, right? Our respiratory fluids are not just water. The other major components of them are salts and proteins. And so when those fluids evaporate, or desiccate is the correct word, then they produce airborne particles. And under a microscope, those desiccated respiratory fluid particles basically look like salt crystals. They're about 80% salt and 20% protein by mass. The biological material itself is less than 1% of the mass of those crystals. So the actual size of an infectious disease particle is irrelevant, mostly, because they never come out to play naked, is the way that I heard it said. They always come out in these little salt crystals. So we're never going to filter the virus out of the air. We're always going to be filtering these crystals out of the air, which, is 100 times bigger or something like that. Now, nearly everything that we do in contamination control engineering follows the law of conservation of mass. This control volume is the mass of air in a room, and conservation of mass states that mass is neither created nor destroyed. It just moves in and out of our control volume and sometimes changes forms. So in the steady state, mass in equals mass out. Mass in is the generation rate, plus any contamination that sneaks in with our supply air, and then mass out is the mass that leaves the room in the exhaust air, plus any mass that falls out of the bubble by deposition. And then biological particles can change form from viable to non-viable. We call that inactivation. And for the purpose of counting infectious mass, we basically count those as having left the bubble. Then we can break the supply and the exhaust terms up into volume flow times concentration per unit volume. And if we're mixing, then the concentration in the exhaust is assumed to equal the concentration in the room. And so we can write out our total equation like so. And then to simplify this, we can assume that the supply air contamination is 0, and then that the inactivation and deposition rates are 0. And that simplifies this equation a tremendous amount, so that the concentration in the room is just the generation rate divided by the airflow. For episodic contamination, we use the room purge equation. This also assumes that deposition and inactivation are 0. And for everyone, including myself, who hate the units of air changes per hour, they really make this equation super easy, and it makes it really easy to solve for air changes per hour in the field. You just take 2 measurements of concentration a couple minutes apart, and then voila, you plug it in and you solve for the air change rate. Now, most airborne transmission assessment doesn't use metrics of particles per cubic meter. We use a metric of quanta. A quanta is the fictional amount of aerosol that creates an infectious dose in a poorly ventilated room. This is the simplest version of a model called the Wells-Riley equation. P is the probability of infection, which is also C over S. C is the number of new cases in a population of S. S is the number of susceptibles. The term on that exponent over there has 5 variables: I, little q, P, T, and big Q. I is the number of infected people in the room. Little q is the generation rate in terms of quanta per hour or per minute. And then P is the pulmonary ventilation rate of the susceptible people. How fast are they inhaling air from the room? And then T is the exposure time, and uppercase Q is our cherished ventilation rate. The units need to line up on that exponent. All the units of the exponent should cancel each other out and leave units of quanta. You can pull out your phone and search the internet right now for quanta per hour, and you'll find some standard quanta per hour rates for diseases like tuberculosis and measles and chickenpox, etc. You'll also find a bunch of papers published in the year 2020. I think there's more hits on quanta per hour in the year 2020 than there has been in the entire span of human history before 2020. But what I think is important to understand is that the term up in the exponent there is actually just conservation of mass again. So here's our volume of air in the room, and we have an infected person or people putting contaminants into the air at that rate of little q. Then we have a susceptible person or people taking breaths from that air at a rate of P, the pulmonary ventilation rate. But of course, the volume of that air changes over time. That's our ventilation rate, uppercase Q, in cubic feet per minute or whatever our units were. So that exponent term is actually the generation rate. That's I times little q. Then the extraction rate, which is P times time, and then our ventilation rate, which is big Q. Now we can make this equation more complicated by adding the deposition rate and the inactivation rate. Those are 0 in this version, but you can find more complicated versions that have those added back in. But before we leave this slide, let's go ahead and reorganize this equation to solve for time in hours with all the other units in minutes. And to make things really, really easy on the next slide, let's assume a probability of P at 10%, and we'll solve the equation for time in hours that it takes us to get to a 10% risk of infection. Now, us HVAC people are most concerned about uppercase Q, the ventilation rate, but we have 100 ventilation rates, right? We have outdoor air ventilation rate, a breathing zone ventilation rate with or without ventilation effectiveness, system outdoor air ventilation rate, total room ventilation rate, zone ventilation rate. Too many ventilation rate. Which one goes here? And of course, the answer is none of the above. When infectious disease people say ventilation, they mean effective room ventilation with uncontaminated air. Those two key terms are effective and uncontaminated. First, they're looking for effective ventilation, which means all of our system and room effects are included. We're looking for the ventilation rate in the space measured by how quickly contaminants are actually removed. And then the second is uncontaminated. Whether it comes from outdoors or the back end of a filter or the room next door, it doesn't really matter. So long as it doesn't have the infectious particle in it, then it is uncontaminated air. So here's a room, and the stick person on the left is producing aerosols, and the stick person in the middle is standing in the plume. Some aerosols come out like projectiles and land right in their face, and there's also a cloud of aerosols that are coming out, and some of those fall to the ground at the desk. You see the little dots on the desk there. A stick person on the right is not in the plume, they are in the room. The biggest thing we can understand here is the difference between the plume and the room. As HVAC people, we can't do anything about the plume. It's like if you go to SeaWorld, if you're sitting in the first 5 rows, you're going to get wet. So the stick person in the middle is standing in the plume of the stick person on the left. There's no HVAC system in the world that can stop them from getting a dose. And I shouldn't have to say this, but also HVAC systems can't remove any of those particles that are on the ground or on the desk. So the only person in this picture that we are concerned with is the stick figure on the right, breathing in the room air, and we want to provide them uncontaminated air into the room. So what's uncontaminated air? Well, first there's outside air that's free of infectious aerosols. And then you can have filtered air. Air going through a filter in the room or directly recirculating gets uncontaminated. A MERV 13 filter removes 90% of those small particles, and a HEPA filter would remove about 99.9% of those small particles. So 90% or 99.99% of those counts as uncontaminated air. You could have a UV system that decontaminates air. You put UV into the top portion of the room, and then the infectious aerosols up there get inactivated, and then that air falls back down in the room, and we consider it decontaminated or uncontaminated air. We hear infectious disease experts say to avoid recirculation, and that's because recirculating contaminated air doesn't count as uncontaminated air or uncontaminated ventilation. So the biggest examples are if this room were cooled by a through-the-wall type unit with no filter and no outside air, that doesn't count. And then also, if you had a desk fan or a ceiling fan moving air around the room, yes, that little scribble that I put there is a desk fan. That doesn't count either, right? So let's do an example using the Wells-Riley equation solved for the exposure time of 10% risk. Stick figure on the right is infected, producing 50 quanta per hour, 0.83 quanta per minute. We'll say this is a 1,000 square foot room with 200 CFM of ventilation with outdoor air. It's on a 3-ton, 1,200 CFM single zone system with either no filters or very crappy filters. And here's our comparative assessment. For the baseline system, our 10% risk occurs at 2 hours. If we upgrade to MERV 13 filters, then 90% of that 1,200 CFM becomes uncontaminated air, and that pushes the 10% risk mark out to 10 hours. We could also convert the unit to 100% outside air. That has basically the same effect. It goes over 12 and a half hours. We could keep the unit as is, but add a 500 CFM HEPA filter into the room. That's pretty good. Moves the risk up around 7 hours. Or we could put UV lights in, giving us an equivalent of 4 air changes of decontamination. That would be 400 CFM, and it would move the 10% risk marker just under about 7 hours, under 7 hours. And the point in this example is that some of these options are equivalent to each other or relatively equivalent to each other, so we can do cost benefit. Changing those filters at the unit in this example may be just a couple $100. Converting the unit to 100% outside air has similar benefits, and temporarily that might only cost a few $100, but once you hit the summer or the winter, that could turn into a big problem. On a long-term basis, a 1200 CFM 100% outside air unit is more like 7.5 or 10 ton and not 3 tons. And so changing that is going to be a project that'll be well over $10,000. A HEPA filter unit that you put in the room would be $1,000, maybe less, but those are quite noisy. And then the UV light system here is probably the most expensive. A permanent install would probably cost $25,000, $50,000. Project costs are more once you get it installed and wired and all that. Editorially, I would want to point out that this example only took about 5 minutes, to point out. And I think 90% of the advice that we should be giving out, if your clients are schools or conference centers or anything like that, could just follow this model, right? Pretty much exactly. But let's take the whole thing to the next level, man. Let's add another room in a multi-room system. Contaminants that move from room to room are called cross-contamination. We'll talk about that a little bit later. Let's talk about recirculated air in a multi-zone system. We'll lay in some CFMs. So our room is 200 CFM. This is a 5-ton unit, so we've got 2,000 CFM overall and 200 CFM of outside air. Stick figure on the right produces 1 million particles per minute, and this room has 200 CFM, and so the concentration in the room is C over G. That's 5,000 particles per cubic foot. Then we could just use conservation of mass to calculate those concentrations through the rest of the system. We just take those particles that move from node to node and divide by the CFM every time to calculate the concentration. Then when we get to the filter, we do a mass balance across the filter, and saying that it removed 90% of particles that came to it. So our supply air has 50 particles per cubic foot. Now, if that number is a concern to you, you can iterate it back through the system. Spoiler alert, the answer is 5,050 particles per cubic foot. You can also set up this whole scenario with conservation of mass by keeping the room concentration and the supply air concentration as 2 unknowns. Then you just write 2 equations and solve for the whole thing that way. Doesn't matter, the answer is going to be the same. The way that I've been doing this year is kind of a simplified method that I'm calling EBDF. I've said it so much that I have an acronym. So EBDF stands for the exhaled breath dilution factor, and here's how it would work. Stick figure on the left is a human producing 6 liters a minute of breath, which is 0.2 cubic feet per minute. Stick figure on the right, the room ventilation here provides an exhaled breath dilution factor of 200 over 0.2, which equals 1,000 to 1. The rest of the air in the system provides an exhaled breath dilution factor of 1,800 over 0.2, which is 9,000 to 1. Our outdoor air provides us 1,000 to 1 dilution factor. And then the air going across the filter gets a dilution factor that's actually a multiplier, so that winds up at 9,000 to 1. And since this is all conservation of mass, all of those dilution effects are additive to each other. So you can just sum up the room, the return, the outdoor air, and the filter for an overall dilution factor of the system. Now, in my opinion, 10,000 to 1 is a pretty good marker here. If your dilution effects are 10,000 to 1, that's 4 orders of magnitude. That's 99.9% dilution, which is the same as a HEPA filter. So in my mind, it's very fair to say that any number over 10,000 to 1 here is very well diluted, and we can consider that recirculated air to be uncontaminated air. Okay, now we got a stick figure on a bed. That means this is a patient room. Let's start by talking about negative pressure. First off, negative pressure only protects the stick figure on the far right, because negative pressure only prevents cross-contamination. So it is totally meaningless to anybody in the room. It only affects people in the room next door. And the second thing to know about negative pressure is that it only works with the door closed. When the door is open, negative pressure is lost. And every time the door opens, cross-contamination occurs. Room pressure does not prevent cross-contamination of a door opening event. There was a really good study done a few years ago where they pushed mannequins in and out of doors and measured the air mixing that occurred between the two rooms. The purpose of the study was to compare sliding doors to swinging doors, and FYI, sliding doors did better. But what the study really showed was whether we're at negative pressure or positive pressure or neutral, whether we walk into a room or out of a room or don't even walk, cross-contamination happens. And it's between 0.5 and 1.5 cubic meters, which is about 18 to 50 cubic feet every time the door opens. The single biggest idea we've seen this year is this one. It's called the ventilated headboard, and I'll show you some pictures of this later. But think of it like putting a kitchen hood right over the patient's head to catch those aerosols before they become part of the room air. That's a great idea, because if we can catch 80 or 90% of those particles and prevent them from mixing in the room, that changes the math, and it changes the math a lot. So we're going to say that this is a 250 square foot patient room with a nurse's station next door to it. The patient room has 300 CFM, the nurse's station has 200 CFM. This system is a central system, so it's got 10,000 CFM of air and pre and final filters, which is just enough to say this is going to be way over a 10,000 dilution factor, and we're going to say the system is providing uncontaminated air. So stick figure in the bed produces 10 million particles per minute. Stick figure in the middle is in the plume. Sorry about that, stick figure in the middle. I hope you're wearing a mask. And then stick figure on the right is getting a concentration of 33,000 particles per cubic feet. Every time the door opens, 50 cubic feet of air mixes between the two spaces. So if we open that door 10 times an hour, that puts 275,000 particles per minute into the nurse's station. The nurse's station is ventilated with 200 CFM, and so the concentration over there is 1,400 particles per cubic foot. And now I'm going to break character and get away from these hand-drawn slides. Fun while it lasted, but now we show a spreadsheet. The units on the y-axis here are particles per cubic meter, which is kind of the more common unit, particles per cubic foot, not really used anywhere. The bar chart on the left is at full scale, and then the bar chart on the right is a logarithmic y-axis. I would normally look at this as a logarithm because you're really looking for those 1 log, 2 log, or 3 log effects. So the first bar here is the base case, the neutral pressure. The concentration in the room is relatively high. It's about 1.5 log reduction to the room next door. The next two scenarios are negative pressure. The concentration in the room next door goes down a little. On the full scale chart, you can see that the negative pressure options actually kind of back contaminate the room based on conservation of mass. Ostensibly, they're pulling particles from the hallway back into the room every time the door is closed. Negative pressure itself doesn't decontaminate the room at all. It just affects the room next door. So the next four scenarios 4, 5, 6, and 7, increase the uncontaminated air in the room. You can add more system air or in-room HEPAs or UV systems, and those all serve to better decontaminate the room by anywhere from 50% to 70%, but none of it really gets to 1 log better. Not surprising, if you want to get 1 log better, then you need to go from 10 air changes per hour to 100 air changes per hour. So it's kind of difficult getting 1 log better. For the stick person on the far right, you can see that decontaminating the room is actually more effective than putting the room at negative pressure. He'll get a lower concentration or a lower overall exposure. And finally, those last two scenarios are the ventilated headboard alternatives. They're modeled as capturing 80 or 90% of the contaminants in the room respectively. The room is still at negative pressure. If you were to capture 90% of the contaminants with the headboard, that does create a 1 log reduction in the room, and the room next door would be another 1 log down from that. So from the perspective of someone in the room next door, those headboard options are pretty clearly the best, right? Even though they're not negative pressure rooms. And I would say the ventilated headboard options also protect, stick figure number 3 here, second from the right. All right. Now we're done with the hand-drawn slides, so let's move into the fun stuff. This is the audience participation slide. Go ahead and pull out your phone and go to an internet browser and type PM 2.5 meter, and then click on shopping. We can get something to measure particles for as little as $50, but I'd recommend spending a little bit more. There are some readily available products that measure PM 10 and PM 2.5 and PM 1 along with VOCs and formaldehyde for about $250, maybe $300. If you want to get a full-blown like banded particle counter to read 0.3 microns and 2.5 and 10 microns, those are about $1,000. The one that our guys have is about $800. And then the like really full-blown 6-band particle counter costs $1,500, $2,500. But you're really not going to need that unless you're certifying clean rooms. While you have your phone out, go ahead and type in CO2 monitor, and you'll see that handheld CO2 monitors can be really cheap. You can get those for as low as $40. But you can buy a pretty good one for about $200, $300. I think the one that I carry is about $300. So the point here, when I used to work with my dad in the garage, he always said, measure twice, cut once, right? Measure twice, cut once. So never cut until you've measured twice. And that's what we've really been emphasizing here to our facilities operations folks. So just to give the example, let's say that a facility is considering changing filters from MERV 8 to MERV 13. Okay, great. Start by going into the building and measuring how well the filters are working. Those indoor levels should be better than the outdoor levels, and on a normal day without fires, or your indoor PM 2.5 should be 12 or less. In my office, it usually runs 5 to 9 or something like that. If it's higher than that, then maybe better filters would be useful, although you'd want to check first to make sure you don't have an internal source of contaminants. If you do change from MERV 8 to MERV 13, that should improve your indoor PM levels by about 50%, and you can calculate that based on the system volumes and your outdoor air percentage. So you would calculate the effect that you expect to see and then test before and then make the change and then test after and make sure that it worked. But most importantly, if you go into a building and your PM 2.5 levels are already below 12 micrograms a cubic meter, then changing filters is not going to do you good. So skip it. Measure before you cut, and if it's already the right length, then please don't cut. This one's just kind of for fun. On the left are the readings I took 2 Mondays ago during the fires. So this was 7:30 in the morning. The reading outside was 72 micrograms of PM 2.5. The reading indoors was 25 micrograms PM 2.5. That ratio of outdoor to indoor particles is about 1 to 3. That's pretty good. That means in my office building the filters are probably working fine. The photo on the right is a particle count in a patient room. This was not during the week of the fires, it was the week before that. But this is right when we walked in before we did any of our testing or any of our fouling or anything like that. There's 39,500 0.3 micron particles. And if you do the math on that, you'll see that this patient room at rest is about ISO class 6, which is very clean. And that's actually pretty common in hospitals. When I take my PM 2.5 reader in there, it very often zeroes out, or it shows kind of 1 or 3 micrograms or something like that. Okay, remember this equation? Let's say we have a room that's contaminated with particles and we take a reading and we get 95 micrograms per meter cube of PM 2.5, then we wait 5 minutes, take another reading, and we get 24 micrograms a cubic meter of PM 2.5. Then we plug in 95 as C1, 24 as C2, and 5 minutes as the delta T. We solve for air changes. It gives you 15, right? Well, that would be my office. I sprayed my office full of Aquanet hairspray and took readings every minute and then plugged them into the equation. I calculated the equivalent air change rate, and you get between 11 and 15 air changes per hour. But I work in a leased landlord-owned office park with like just standard issue rooftop VAV units. I assure you, my office does not have 15 air changes per hour. I did the same thing with CO2. You can foul the space with CO2 using dry ice. You can also do jumping jacks or try the old baking soda and vinegar trick, but speaking from experience, use dry ice. It's very easy. Again, the results don't behave like the equation predicts. It starts off looking fantastic, 13 or 15 air changes, which is not true. And then it trails off to 2 to 4 air changes, which is true. That's the actual supply rate. But then it trails off again, and it trails off to like a half of an air change. And I was actually really surprised how long that last bit of contamination stayed in the room. This is with the door closed. And eventually I just kind of got up and went and got a donut. But it brings up this interesting idea that we could see sustained or sustainable low differential concentrations across a closed door like this that never resolve or take a long, long, long time to resolve, much longer than our equations would predict. I think that's worth more investigation. This is a screening area with 1,000 CFM HEPA filter unit blowing clean air around the space. So to test this, we found the area of one station with a 10-second spray, Aquanet hairspray. Baseline test without the HEPA showed 16 equivalent air changes. That's better than it should be. The space only really has 6 air changes. And then with the fan on, it went up to 20 to 25 equivalent air changes. So it went up about 5 to 10, but it should have gone up 15. This is only a 300 square foot space, so 1,000 CFM is more like 15 air changes. And the orientation of this HEPA unit in the space, i.e. the direction we pointed it, made a big difference, particularly in the immediate reaction to the fouling. You can see scenario 2, it has a big spike, which is caused by the air path. Here's 2 versions of those ventilated headboards, so now you can see pictures of them. And we tested these with theatrical smoke. We had a theatrical smoke machine. We just blew a bunch of smoke at them and then measured the particle decay. With the HEPA filters running, they increase the overall effective ventilation in the room. But once again, the performance doesn't match the calculations. This time it goes both ways. On paper, the HEPA filter should be adding 15 air changes to the room. In reality, one of these added 10 air changes and the other added about 20 to 25 air changes. So to generalize some of the lessons that we're getting out of this particle testing, my opinion at this point is the baseline performance of kind of your room is likely to be better than your equations predict. But then the marginal improvements, at least most of the marginal improvements, tend to underperform based on what you would predict. And then the other thing is we need to understand doors quite a bit better. This is a science project I did in the office. I went into my pal Joe's office, Joe Stasny, and I put a shitload of dry ice in there. I got it up to 4,000 ppm and held it there for a half an hour. I took CO2 readings just outside of the office. There's a bookshelf right outside of his office, and then there's a cubicle right outside of his office. And those results don't actually show cross-contamination. Our office normally runs between 500 and 700 parts per million. It never really moved out of that range, even though there was this Halloween party of dry ice going on behind the door. So this test kind of suggests that a closed door can be a very effective barrier against cross-contamination. Then we have this test. To contrast, this is data from a patient room. We had one particle counter in the middle of the room, another particle counter in the hallway, and the goal was to see if we could leave the door open with the headboard on. We fouled the room with hairspray for 15 minutes at a time and tested different scenarios. But in this test, we got particles in the hallway in every case. There were always 1 log less in the room, so that's good news. But headboards on, headboards off, doors closed, doors open, didn't matter. We always got particles in the hallway. I should say that this is I consider this to be a failed headboard test. If you remember the calculations I did 6 slides ago, we want those headboards to capture 90% of the particles generated underneath them. Hey, even 50% would be something very worth talking about. This data doesn't show that at all. And in review, the test is totally wrong. We tested this with hairspray. You can kind of see me with a can there spraying it. When you put a can of hairspray at pillow height and then spray it out into the room, you're just contaminating the room. There's way too much velocity in that spray for the hood to ever capture it. So the next time we're going to go retest this, and next time I think we're going to use these little residential room humidifiers, from Walmart, and fill them full of salt water. So remember, desiccated respiratory droplets are largely salt. So salt water is actually a pretty good proxy. And I was able to prove in our conference room last week that you could definitely contaminate a room with a humidifier full of salt water. So let's sum up a little bit. In the last 9 months, HVAC engineers have been doing a lot of things to our systems in the name of infectious aerosol control. But the vast majority of activity that we've seen in 2020 has been uncalculated, non-comparative, and unvalidated. I wanted to take today and to talk about calculations, about comparing options, and then about validating performance. It's always bad to point out your own jokes, but there were 2 subliminal messages in this presentation I'll go ahead and point out just for fun. First off, those slides were hand-drawn as if they were hand calculations. And this is 2020, guys. We have very, very sophisticated calculation and modeling tools. We have CFD, multi-zone contaminant modeling. We can simulate characters walking around spaces and tabulate their daily exposure levels. We can do amazing things with very sophisticated calculation tools. But so far this year, it's like nobody's doing any of that. So compared to what we've seen, hand calculations would be a big improvement. Then the other little game I played with this presentation is this. This is the first time that I'm saying the word COVID-19, and I did that on purpose too. I think you'll hear a lot of people in the HVAC industry say that, you know, we can't calculate or we can't compare, we can't validate anything because there's too much scientific uncertainty about COVID-19, and I think that's bullshit. It is true that the scientific headlines seem to, you know, shuffle around once a month, but uncertainty is not an excuse to skip calculations or skip comparisons or skip validations. There is plenty of great engineering we can do in the face of scientific uncertainty. And let me go ahead and stop there.